We're going to take a look at an optimization problem, and in this optimization problem we're going to be enclosing a field by a fence. One side of the field is against a mountain and thus does not need any fencing. We have 600 feet of total fence to work with, so we want to find the dimensions that will give us the largest possible area. Now there's some steps we want to adhere to when doing an optimization problem. First, when possible, we want to draw a diagram of what's going on. Then we want to label any unknowns. Then we'll create a function to optimize. That is our objective function. When possible, we create a constraint equation, and we'll use that constraint equation to get the optimization function in terms of one variable. Once we have that, we optimize using calculus. So here's our diagram. We have the mountain on one side and then our rectangular fence. Now we don't know the dimensions of the rectangle, so we'll represent those with unknowns. So perhaps we use x and y. Now we need to come up with a function that we're going to optimize in terms of our variables. Remember what it is we want to optimize. In this case, we wanted to maximize area, so we need a function for area. Well, area of a rectangle, in this case, is x times y. So a equals xy is our objective function. Now, let's see if we can come up with the constraint equation, because what we saw is our objective function was in terms of two variables. Well, remember, we only have 600 feet of fence to work with, so if we add up x plus y plus x, it can only equal 600 feet. Simplifying, we get 2x plus y equals 600. That's our constraint equation. Now, we want to get our optimization function in terms of a single variable. So what we do is we solve our constraint equation for one of the variables. We can choose either x or y. In this case, it looks like it'll be a little bit easier to solve for y. So what we'll do is we'll solve our constraint equation for y and then sub that into our objective function. So solving our constraint for y, we get y equals 600 minus 2x. Now we're going to substitute that in for the y in our area function. So we get the following. The area in terms of x is 600x minus 2x squared. Now since x represents the length of a side of fence, the smallest it can be is 0, and the largest it can be is 300. Because if x is 0, we have no area, and if x is 300, we actually have no area as well. So what we have is an extreme value problem, because we want to maximize a function, a continuous function, on the interval from 0 to 300. Remember how we do that. First off, we find any critical points by taking the derivative. Now the derivative is 0 when x is equal to 150. So 150 is a critical point. So we're going to evaluate our function for area at x equals 0, x equals 150, and x equals 300. Well, at 0 and 300, we get an area of 0, so those are not going to be the maximum. At 150, we get an area of 45,000 square feet, which will be our maximum possible area. The extreme value theorem guarantees us that. So now let's just go back and find our dimensions. Since x was 150 feet and y is equal to 600 minus 2 times x, we find that y is equal to 300 feet. So our maximum possible area is 45,000 square feet, and the dimensions on that are that the walls that come out from the mountain are 150 feet, and the wall that's parallel to the mountain is 300 feet.